Okay, so we'll start in one. We'll start. Thanks. All right. So today, we're finally getting to some very interesting theorems. In particular, I think maybe a week from now, maybe even before, maybe already next week, we'll prove the fundamental theorem of algebra. That every polynomial over the complex numbers with just one variable has a zero. Okay, this is one of the main theorems in algebra, and all this buildup that we're doing, we're actually quite close to proving it, right? Using only analysis. Okay, so where we ended last time on Friday was Cauchy's theorem on a disk. Okay, and I basically argue that we had already proved it, right? That if, but I'll do it a little more carefully now. Okay, but right. So the theorem says that we consider an open disk, right? So let delta be an open disk, or by this I just mean the disk centered at z0 and with radius r. Okay. If a function f is analytic, going from the disk to the complex numbers is analytic on delta, this is just what I had on the board on Friday, and we have a closed curve inside the open disk, then the integral over this closed curve is 0. Okay, so we did this for the rectangle, not just any curve in the rectangle, we did it where the curve was actually the boundary of the rectangle. Okay, and now the idea is to use that to prove this over the disk, where any curve inside of the disk will have integral 0. And what I pointed out on Friday is that we basically had already done this, right? When in the language of integration over the reals, we argue that having a primitive or being an exact differential was the same thing as integrals depending only on endpoints of paths, right? If you recall that proof, we proved that those things were equivalent, right? And so if we had a primitive or if it was an exact differential, then integration over a curve depending only on the endpoints, right? We proved that for any curve. But then the converse of that, we actually only use curves with polygon lines, and in particular only with horizontal and vertical lines, right? And so really what we also showed in that equivalence was that if the integral doesn't depend, right? If the integral depends only on endpoints for curves that are just polygon lines with horizontal and vertical lines, then it must also only depend on the endpoints for any curve, right? And really, this is all we're doing here now, right? Because the rectangle gives us that the integral only depends on the endpoints for horizontal and vertical polygon lines, right? Because, right, if you think about the rectangle going like this or going like this would be the same, right? The integral over this curve and the integral over this one would be the same, because going like this and then minus that one was 0, right? And so the rectangle gives us this knowledge that integration over vertical and horizontal lines only depends on endpoints, and then we can use that argument to push for any curves, right? But let's just do it a little more careful, just to point out that we've already done that. Okay, so let's say proof, right? So we want to show that it only depends on the endpoints, right? So we want to show that it has a primitive in this language, that it is an exact differential, right? Another way of writing this, right? This is the language that we were using more for integration over the reals, right? Thinking of real and imaginary part as just two components over the reals, right? But what I mean by this is, right, that exists f of z, right, such that the derivative of f of z is equal to our function, right? That the function has a primitive. Okay, so how do we do this? We do this exactly how we did it when we talked about exact differentials over the reals, right? We just construct this, right? So let's take our disk. Okay, so the inside of this is our disk, and let's take z0. Okay, and now for any z, let's say that this is z, right? We can take two curves, right? We can take the curve that goes up to here, right, with say 90 degrees. Okay, let's call this gamma 1, right? And we could define f of z, right, as just the integral, right, over gamma 1 of fz dz. right? Okay, and this is well defined, right? For any point in the disk, I can always go to it by taking first an horizontal line and then a vertical line. Right? Now, if we look now, because of the theorem over, let me go to another color. We know that this is exactly the same as if I were to integrate over a curve gamma 2, right? This is the same as integrating over a curve gamma 2 f of z dz. Why? Because the integral around this rectangle that was formed is 0, right? If I think of this as a rectangle R, right, the integral, right, with this abusive notation of the, using the abusive notation of the integrals, the integral over gamma 1, right, minus the integral over gamma 2 is just the integral at the boundary of the rectangle, right, for any analytic function in an open set containing all of this, which certainly is the case for f, because this integral on the disk is analytic on the disk. And so because this integral is 0 by Cauchy's theorem on the rectangles, we know that these two integrals need to be the same, right? It's just a way of making formal what I said, that the integral that only depends on the endpoints of the path if it's only horizontal and vertical lines. Okay? So f of z is both equal to this and that. Okay, so far so good. Okay, but now if I think, if I use the first definition, right, if I take f of z, right, the integral over this gamma 1 of fz dz, okay, maybe I should, I have a bit of abusive notation here because I have the z inside and the z outside. Let me call this z prime. Or let me call this z1 just so that I don't have this issue. Okay. Okay, but now in the way that this is defined, this is of course a function of z1, and its derivative with respect to x, right? Right, what is its derivative with respect to x? Right? I'm integrating here, and then I'm integrating up. Oh, sorry, with respect to y. Right? So I'm integrating, right? I'm integrating here, and then integrating up, right? So here I only have the I dy, and so if you work out the derivative, what this is just I f of z. Right? Is that clear? Because, right, as I'm going up, we can take, right, dz, it's dx plus I dy, and so this derivative in this path will just be by the fundamental theorem of calculus, will just be fz, right, and gets the y because of the dy. Now, if I do it on the other definition of f of z, which is equivalent, right? Guess I should have done this one first. So. Right. Right, it's exactly the same calculation that we did when we talked about the exact differentials. Right, is equal to f of z1. Right? Because when I take the, right, if I look at the derivative with respect to the variable x, to the real part, right, and going this way, then the derivative, of course, when I integrate over the green line by the fundamental theorem of calculus is just f of z, right? And then what I do here is I f of z, right? Because recall that dz we can write as dx plus I dy, right? The same thing that we did for the exact differentials. Okay, but now what we have, right? We have that the partial of y of f, okay, at the point z1, right, is equal to I times this one, x, f of z. Yeah? Right? And these were exactly the Cauchy-Riemann equations. And so f, right? And so we know that f is analytic. And right, because of this here, we know if we take the derivative of f, right, if it's analytic, the integral is the same regardless of the direction that I take. So I can just take it right over the reals, and so right, the derivative is f of z. Okay. Okay. I think this was the last time that we need to go back to the reals to talk about integration. Okay. Okay, so this proves Cauchy theorem on the disk, right? And why is this crucial? Right, and again, remember, the one on the rectangle had an idea, this one really didn't, right? This one was just sort of was already done once the one in the rectangle was done. And we also did that one in the rectangle where we could take exceptional points, right? Where the exceptional points needed to satisfy a certain limit. So we're going to do that also for the circle. And I saw, actually, before I started, I looked at, there was on the forum questions about why did we consider this kind of exceptional points. This will become clear in a second. Okay. So maybe before I go to the exceptional points, I want you to take a second to think about what did we really use about the disk here, right? The only thing that we really used about the disk here was the fact that, right, there was a point like that we considered the center, but we could have taken any other special point, fixed point, right, that we take fixed. And then all we needed to do was to go towards z, or z1, right, by horizontal and vertical lines, right? So, of course, if you have an ellipse, you can still do this, right? If you have a square, many different regions, you can do this, right? It's a bit less clear how to do it if you have, weird shapes. Like, for example, I don't know, if you have something like this, right? It's a bit clear how to do it, but you can imagine that you can probably do it by going with horizontal and vertical lines around the obstacles, right? And this is something that we're going to develop. Okay, but for an ellipse, certainly the theorem also works, right? There is nothing changes. It also works. Okay. All right, so let's erase and let's prove the theorem now with these exceptional points, because actually we're going to use it. And then we're going to do a little bit of plane topology. And again, this is a theorem that doesn't really have an idea to prove it. It will be useful. Theorem. Okay, let omega be a region obtained by obtained, say, from a disk, an open disk. By removing a finite number of points. Okay, say k from 1 to some big set k. Okay, points. Right, if f from this region to the complex numbers is analytic, and for all one of these k's, we have that this limit is exactly the same thing as over the rectangle. And again, the proof doesn't really have an idea, but it'll be very useful to have. Okay, let's see. Okay, limit of this of z minus ck f of z is 0. Then, okay, I should say, and this a closed curve in omega, then the integral around the curve is 0. Okay, so it's just the adaptation of Cauchy's theorem to right. It's just the adaptation of Cauchy's theorem to allow for these points, right? Okay, so again, the proof doesn't really have. Maybe before proving it, I should make a comment answering this question that was in the forum. Oh, I think someone in one of the chats was asking what this means. The delta is just the name I'm giving to the region that there's an open disk, right? So delta is just a subset of the complex numbers, and is just given by all complex numbers z, such that z minus z0 is smaller than some r, right? Of course, depends on z0 and on r. Okay, so maybe before we prove this theorem, which also has a straightforward proof, let me just say, why is it that we care? Why is it that we're going to care about such functions? The reason why we care about such functions is that it's going to allow us to talk about derivatives, right? So here's the reason, and you'll see this in a bit. Just giving a bit of foreshadowing what's to come. If I take a function like this, say f of z, like the approximation of the derivative at a point A, say. Let's say f is continuous. Right. And let's say I take this this function f. Right? Okay, or let's say that f is analytic. Okay, let's say f is analytic in some disk, and now I take this function big F. Maybe big F is not a good thing to call it. Let me call it g. Okay, I take this function g of z. This function is of course analytic outside of A, but in A it's not even well defined, right? Because I'm dividing by 0. However, it's clear that that limit, right? The limit as z goes to A of z minus A g of z is just the limit as z goes to A of f of z minus f of A. But if f is analytic, in particular, it's continuous, and so this is 0. And so for this function, A is an exceptional point of that type, and this is going to allow us to talk about approximations to the derivative. and use all those theorems for this function, which would allow us to actually say a lot about derivatives of analytic functions, right? That's the reason why we care about these kind of special exceptional points, right? Because it will allow us to talk about derivatives, and this is how we're going to get things like an analytic function can be differentiated many, many times, and theorems of this style. Okay, so let's prove that theorem. I mean, the proof is sort of exactly the same. I'm going to do the proof by picture. Right, so we're going to build the derivative exactly the same. So let's take z0 here. Now I can call it z because right, I can call it z because I'm not even going to write the integrals. Right, we just have to define f of z. Right, we just have the same way. Maybe I'll still call it z1. We'll just have to define f of z1 the same way as an integral around the curve, right, of f of z dz. But now we just have to be a little more careful about what curves we consider, right? Because if there is, we can't just take, if there is an exceptional point here, right, we can't just take a curve that goes through an exceptional point, right? But we can just take curves that have, say, a point in the middle, like a line in the middle, right? They just go up and then to the side and then up again, or say, to this, maybe let me use another color, right, to the side, up, and then again, right? And because of these theorems, because of the theorem over the rectangle, even if there are bad points in between, let's say that there's a bad point here, another bad point, I'm putting this, right? So let's say that this is C2, then even if there's a point in between, right, taking this one or taking this choice is exactly the same, because the integral over this rectangle is still 0, even with an exceptional point, right? Because we know that the theorem, the integrals over rectangles with exceptional points of that type are still 0, right? So this construction, right, this construction doesn't depend on the middle segment, right? Otherwise, it wouldn't be well defined, right? We need to define these things, right? Need to be well defined. Doesn't depend on middle segment, right? And so this is all well defined. And of course, the derivative again. If you end up with an up line segment, you get the derivative like the right. You get that the partial is if. Right, if of z, and with an horizontal you get the f of z, so you get exactly the same thing, right? Now, you just have to be a little more careful okay, and so I guess I should say, what's really important here is the theorem, that theorem for rectangles, for sides of rectangles, right? If you have some kind of other weird point, right, where this limit does not hold, we know that the integrals are not necessarily 0, right? And so this proof couldn't possibly work. But the reason is that we also didn't have that theorem for the rectangle, right? But because we have that theorem for the rectangle, as long as we take one of these pictures that avoids an exceptional point in the center, then we're always okay, right? Now, there is sometimes you have to be a little more careful, when making this precise, right? Because if there is a point in, if there is a bad point here at the same, say, real, let's say that there's a bad point here with the same imaginary part as z, you may have to take other, right? You may have to take 4 segments, right? Because you can't go up and then go over this point, but again, you just take another segment and everything works out fine. Okay, there's many ways of coming up with this picture. You could also, for any closed curve, take another disk where the center is a little off, but the disk still contains the curve. And then with that, you could assume without loss of generality that there's no bad point with the same real or imaginary part as z0, and you wouldn't have to, right? And you wouldn't have to avoid said point, and you just need to avoid above. Okay, but this is you just need to be a little careful about how you construct this. Okay, but the key thing is that, again, because the integral doesn't depend on the path for horizontal and vertical lines, even if it has points in the middle of the prescribed rectangles that satisfy that where the function is not well defined, but as long as this limit exists and is 0, then we're okay. Okay, so you can take a look at the book for more, things in more detail, but this is proof by picture. Okay, but of course, this can be made absolutely precise. Just be a while to, define exactly. Okay, all right. But I still recommend, sitting down and trying to really convince yourselves that this is a precise enough argument, right? This is a good exercise to do. It's not necessarily the most useful time of lecture for me to be, defining all these paths and so on while they're all watching, but you should definitely sit down and try to do this. Okay. All right, so now I think we're ready for some different things. And in particular, we're going to work towards an integral formula, right? So in a way, right, I sort of hinted at this already, that because of this fact that these curves don't only depend on the endpoints, and because the integral of 1 over z minus a is 2 pi I, that we're going to be able to massage that and get a representation formula in which we get the function value at a point to be equal to the integral of the function at some curve around that point, right? And so the goal now is to go towards an integral formula. But first, we're going to talk a little bit about winding numbers, right? It's all going to go back to this fact that if I have a circle, right? So now we're going to talk a bit about topology. Okay, so take a circle, take a point A, the complex plane, and take now a circle with some radius, right? So the circle will be all points z such that z minus a is exactly r, right? So this is a circle of let's see where I have a circle of radius r and center a. Okay, so I have a. Okay, and so what we saw is the integral of the circle 1 over z minus a dz, right? That this was 2 pi I. Okay, and I said that this was going to be very useful in what follows. Okay. And in fact, we're going to want to talk about, right? The idea being, let me see if I can give some intuition of what's going on here, right? If instead of a circle, I take the circle twice, right? I loop around twice. Then instead of 2 pi I, I'm going to get 4 pi I, right? So one might intuitively be led to believe that somehow the multiple of 2 pi I that I get is counting how many times a curve, right? How many times some curve is going around a point, right? Which can tell me a lot of topological information about the point, about the space in which the curve is defined, and so on and so forth, or geometric information as well. Okay, so there's sort of already an intuition that somehow this should be counting roughly how many times I'm looping around this circle. And in fact, this is why these are called winding numbers. But we're going to want to define these not just for the circle, but any curve, right? So let gamma be a closed curve, right? They're always piecewise differentiable. Okay. Right? We want to define an object which is 1 over 2 pi I okay, so of course, for this to even be well defined, we need that A is not inside the curve. I mean, it can be inside on the interior of the interior region defined by the curve, but it cannot belong to the curve, right? The curve is not allowed to go through A, otherwise we have trouble integrating this. Okay, but we want to define this as sort of the number of times that a curve goes around the point. Okay, and we're going to define this as the winding number. Okay, so this, I never remember if in the winding number the curve or the point goes first. The curve goes first. Right, and this is called the winding number. Okay, so I've defined something without justifying very much. I will in a second. Right, but coming from this intuition that the integral around the circle is 2 pi I, if I go around twice on the circle, it's of course double that and so on. Then given a curve, I want to still talk about how many times I go by, and the good candidate is to make a definition like this. Now, in order for this to make any sense, right, it better be an integer, right? The curve shouldn't go around the point 1.5 times, right? So I need to show that this is an integer, and I need to convince you that indeed this corresponds to how many times goes around, right? So we have a definition here, but I have to justify that this is well defined. Okay, so let's start proving properties of winding numbers. In particular, let's start by proving that this is actually an integer always. Again, we have to do just that analytically. Okay, so first theorem. Okay, again, a complex number, closed curve, such that A does not belong to gamma. I want to prove that 1 over 2 pi I of 1 over z minus A over gamma dz is an integer. Okay, so how do we prove something like this? I mean, there's a trick. Right, so we have to prove that this integral is a multiple of 2 pi I. Right, what's one way that we can prove that something is a multiple of 2 pi I, a complex number? Like, what's a natural way? Right, so okay, so let's put some, let me try to give some intuition. Right, the goal is to show that is a multiple, is an integer multiple. I mean, I'm just rewriting, but of 2 pi I. I'm just rewrote. But how can we, using complex analysis, how can we argue that a number is an integer multiple of 2 pi I? Right? We don't have access to like number theory to talk about integer multiples and what's an integer, what's divisible, and so on. Right? That hasn't yet been part of the language of complex analysis. But as someone said, exponential. Right? Exactly. Right? So how can we do this? Right? The exponential idea, right? The idea that was given in the chat was the exponential, right? If the exponential of z is 1, right, then it must be that z is an integer multiple of 2 pi I. An integer multiple of 2 pi I. Right? And this will exactly be the idea. Okay, great. Thank you for the suggestion. Okay, so now there's, a bit of a slick trick. So let's take the parameterization, the t, like the parameterization of, parameterization of gamma. Okay, and now we defined a new function, h of big T, right? In the book, the author uses a lot the abusive notation of the letter inside the integrand being the same as outside. I'll try to separate them just to avoid confusion. Okay, so this goes from alpha to big T, right? I'm going to integrate over the curve, but not necessarily the whole curve. I'm just going to integrate from alpha until a point big T. Okay? And now the integral will be, will be the integral of that, right? So z prime t over zt minus a dt. Okay, so ht is just the integral of, right? It's just the integral of the curve up to t. So fact, right? Just collecting facts. So h of alpha is 0, right? And h of beta is our goal, right? So let's say, okay, h of beta is, yeah, let's just write it, okay. Gamma 1 over z minus a dz. Okay, now for the points, right? Gamma is piecewise differentiable. So for the points, right? So for the points t such that z prime of t is continuous, right, which must be almost everywhere, then we have that the derivative, again, fundamental theorem of using again the fundamental theorem of the calculus, h of t is what is just given by, right, the integrand. So z prime of t, right, times, right, we want to show that the exponential of this is the same thing as the exponential of that. So we're going to show that the exponential of h of t as derivative 0, right? This is the goal. Okay, so let's do it. So z of t minus a okay, maybe I should, okay, I don't want to just write the trick. I want to make sure that the proof makes, these things sometimes are presented like there's some kind of, magic trick, but there's always an intuition behind, or almost always. Or I should say, there's always an intuition behind. Not always is easy to explain, but here it's easy to explain, right? The goal is to show that the exponential of h alpha is equal to the exponential of h of beta, right? And so I'm going to try and show that the derivative, let me use this language, right, of exponential of h of p, exponential of the exponential of h of t is 0. Okay, turns out that, okay, it's easier to do with the minus, but that doesn't make a difference. Okay, if I could show that something like this is 0, then I would be done. But what's the problem with this? Why doesn't this quite work? Right? The reason this doesn't quite work is that I don't actually have anywhere that, right? I don't actually have anywhere that the path is closed, right? It's important that the path starts and ends in the same place. Right, and so really the function that we need to take the derivative is something that somehow needs to capture that information, right? The one that works, make sure I get this right. Right, if I can show that the derivative of this is 0, then, right, because this is continuous, at least almost everywhere, then this function needs to be constant. And so if this function is constant, because both at t equals alpha and t equals beta, the curve needs to be in the same place. So this value is the same. So the exponential is the same. And so this would be this would imply, right? This implies that it's a multiple of 2pi, and so now we just have to look at what that derivative is. And we worked out things so that everything would cancel out. Okay, so let's take derivatives. So let's make sure I have okay. Okay, so this is equal to, right? So I take first derivative here minus the derivative of ht times exponential minus ht okay, plus, now I take the derivative of the other one, so I get exponential of minus ht, and now I get just z prime t, right? But h prime t times zt minus a, right? By definition, this times this is just equal to that, right? At least on the points it's continuous. But this is equal to 0, at least in the points where z prime of t is continuous. Right? Because the curve is piecewise differentiable, this needs to be almost everywhere. So, right? So this function must be constant, right? So this function must be constant. And so if this function is constant, it means that, let me see, I'm running out of chalk. It means that exponential of minus h alpha times z alpha, right? Z alpha minus a needs to be equal to exponential of minus h beta times z beta minus a, right? But a is not in the curve, so this is non-zero, right? This and this are equal, right? Are equal, right? Because the curve is closed, so the point z alpha is the same as z beta equal, and they are not 0, right? Because a is not in the curve. So this means that exponential of minus h beta needs to be exponential of 0, because h alpha is 0, right? It was exactly what was proposed on chat. This is 1. Therefore, h of b is an integer multiple of 2pi, right? By the orange idea. Okay, and we are done. All right, so at least this is an integer. Okay, check. So that's a good start. And now we're going to, after the break, we're going to prove other things about this number. Right? There's other things that we'd like to argue are true. For example, it better be that if I have a curve, right? If I have a curve and I look at the winding number of the curve with respect to this point and with respect to another point, right, that's in the same region as determined by the curve, it better be that it doesn't change, because the curve goes around this point as much as it goes around that point. And so we're going to prove that in particular using analysis. Okay, so I'll leave Zoom on. I'll close the YouTube stream, and there's already the part 2 link available, and we'll start in 15 minutes or so. All right, thanks. If there's questions, I'm around.